Now operators now all the three operators are arranged in the same line. Hence the light which is coming out from the laser source, it's made to pass through the grating. Okay, you can see that through the grating the light pass. Then that light which it comes out here, it gets diffracted. It gets diffracted here. Okay, so on the screen, if you see on the screen, you will see that the light spots, okay, the diffraction spots you will see on the screen like this. Okay, so in this you must identify the central spot and mark that central spot as shown here. The mark that central spot as C and the value correspond to that as 0. Then on either side with a pencil, if this is the central spot, coincide that central spot with the cross section lines drawn. Then on either side you mark 1, 2, 3, 4, 5 like this. And the other side also 1, 2, 3, 4, 5 like this. You put a point and then take out this graph sheet. Okay, after this you need to measure the distance between the first two consecutive diffraction patterns distance, then the second spots, that is second diffraction spots, third, like this you need to calculate. Here you can see the central spot is marked for a particular distance of 90 centimeter. This distance is the distance between the grating and the screen. Okay, so here with the help of this scale, the distance between the grating and the screen, it is adjusted. Screen and the grating. So the grating, you must take this position as a reference, then corresponding to that what is the value. It may be 80 or it may be 90. Like this you can vary the position of this grating and you can adjust the distance. Okay, so like this here we performed it for we informed you to perform it for two distances. One is for 90 centimeter distance and the other one is for 80 centimeter distance. So for 80 centimeter distance you can see the central spot here, the C. From here the first left and first right spots are this diffraction spots there. Okay, so the intensity of first right and first left spots are lesser compared to the central spot. Next is the second left and second right. Okay, the intensity of this second diffraction pattern further reduces. Next, third to third, fourth to fourth, fifth to fifth. Like this you measure the distance and call that distance as 2xm. So that 2xm you call it as 2x1 for the first, and then for the second 2x2, for the third 2x3, for fourth 2x4, like this. And tabulate these values in the tabular column. So here is the tabular column. So in this tabular column, for 80 centimeters, you have a diffraction different diffraction orders like 1, 2, 3, 4 for 4 orders. The 2xm value, that is from left spot to the right spot, it is 2.2 centimeter here. For the second order 4.4, for third order 6.4, fourth order 8.5, like this. Half of this will give you the average value of the distance from the center spot to the first order diffraction spot, then from the central spot to the second order diffraction spot, from the central to the third order diffraction spot, from the central to the fourth order diffraction spot. Okay, now here you can see this one, how it happens. So once the light passes from this grating, then it get diffracted. So if C is the spot corresponds to the first order diffraction on one side, B is the central spot in this, and A is the spot where the light gets scattered from the grating. So now if you see this one ABC, it makes a right angle triangle. Then the angle of this triangle, you can determine this BAC angle by knowing the value of BC and by knowing the value of AB. AB is the distance from the grating to the screen. Okay, grating to the screen, the direct distance, which we kept it as 80 centimeter. And then you know the distance BC. BC is nothing but it is XM. So you took from C to C dash, from here to here, that one you divided by 2 to get this from central spot to the first order spot. Okay, so BC is XM, right? So here first order means x1. So you know the value of x1 and you know the value of AB. AB is common for all. Okay, for 4 trials. For next 4 trials, AB value is changing from 80 to 90 centimeters, right? Now BC distance for the first order, it is 1.1, right? And this is the value of R, that is distance between the grating and the screen. So when you substitute these two values in this formula, tan inverse of xm by r, because tan theta is opposite side by hypotenuse, right? So opposite side of an angle theta is BC divided by adjacent side is AB. So opposite side by adjacent side is nothing but tan of an angle. So tan of an angle is equal to opposite side by adjacent side. Then only the angle of diffraction theta m if you want, then tan inverse of xm by r. So here it is tan inverse of xm by r. Okay, then with the help of this you can calculate the theta values. Next, similarly for the next distance, that is for the distance of 90 centimeter, you can determine the theta values. Okay, once you know the theta value for different order of diffraction, this is what it is mentioned as m. So in that formula, lambda is equal to d sin theta m by m, where d is the grating constant which I showed, and its value also I showed, right? How to calculate I showed. So d is known, theta m is this, and m is corresponding to that 1. So for the first trial it is 1. For the second trial, m value becomes 2 and theta m becomes this value, that is 1.575. For third trial, m is 3 and theta m is 2.291. If you substitute these two values here, then you can calculate the wavelength. One example of calculation it is showed here. Okay, like this. See, lambda is equal to d value is 5.08 into 10 to the power of minus 5 meters. Sine of the angle, that is 0.788, divided by order of diffraction is 1. So by simplifying you get wavelength as 6.986 into 10 to the power of minus 3. Similarly for the second order diffraction, 2 is the m value and theta corresponding to that it changes. You get 6.681 into 10 to the power of minus 7. Similarly for third order, m equal to 3 and its corresponding theta. Okay, so the d remains the same for a given grating. Like this, when you evaluate, you can see that all the lambda values are same, right? So all the lambda values are in the range of 6.986, 6.981, 6.761, 6.737, like this. So there is a consistency in the readings. Then you can take the average of these values as the final answer and express that in nanometers. So the final answer is 681.8 nanometers. Okay, so the average wavelength value of a light source, the laser light source, is 681.8 nanometers. So just by seeing the answer only you can guess the answer is right or wrong, because for observing the laser light it looks red color. So red color light means the wavelength of red color light is in the range of 6500 to 7000 angstroms, or 650 to 700 nanometers. So you are getting near to, in between that range. That means it is for observation what we are seeing the red color, the same thing it matches with this finally calculated answer. In that way, once you determine the average wavelength of laser light source, then you need to write it in the result. So in the result you write the wavelength of given laser light source is 681.8 nanometer. It is the average wavelength. So here are some of the precautions. That precautions means Here you must keep all the things in the same line, and grating must be fixed properly to the grating holder, and make sure that the laser light undergo diffraction after passing through the grating, so that you will see many number of spots in the grating. When you mark the spots on the graph sheet, you must be careful. It should not disturb the setup. You need to mark the spots with the help of pencil, and then take out that. After that you draw lines and then mark all the distances precisely. You measure the distance. So how accurately you make all the alignments, and then how exactly you measure the distance, that will indicate your wavelength value. So if there is a consistency in your final answer for all the different trials, that means what the marking you made in the graph sheet and then what the arrangements you made is perfect. Okay, so thank you.